By now, you've seen a range of different learning algorithms. Within supervised learning, the performance of many supervised learning algorithms will be pretty similar, and what matters less will often be whether you use learning algorithm A or learning algorithm B, but what matters more will often be things like the amount of data you train these algorithms on, as well as your skill in applying these algorithms, things like your choice of the features that you design to give the learning algorithms and how you choose the regularization parameter and things like that. But there's one more algorithm that is very powerful and is very widely used both within industry and in academia, and that's called the support vector machine. And compared to both logistic regression and neural networks, the support vector machine, or the SVM, sometimes gives a cleaner and sometimes more powerful way of learning complex nonlinear functions. And so I'd like to take the next videos to talk about that. Later in this course, I will do a quick survey of a range of different supervised learning algorithms just to very briefly describe them. But the support vector machine, given its popularity and how powerful it is, this will be the last of the supervised learning algorithms that I'll spend a significant amount of time on in this course. As with our development of other learning algorithms, we're going to start by talking about the optimization objective. So let's get started on this algorithm. In order to describe the support vector machine, I'm actually going to start with logistic regression and show how we can modify it a bit and get what is essentially the support vector machine. So in logistic regression, we have our familiar form of the hypothesis there and the sigmoid activation function shown on the right. And in order to explain some of the math, I'm going to use Z to denote theta transpose X here. Now, let's think about what we would like logistic regression to do. If we have an example with y equals 1, and by this I mean an example in either the training set or the test set, or the cross-validation set. But if y is equal to 1, then we're sort of hoping that h of x will be close to 1. So, right, we're hoping they'll correctly classify that example. And having h of x close to 1, what that means is that theta transpose x must be much larger than 0. So this greater than sign, that means much greater than 0. And that's because if it's z, that is theta transpose x, is when z is much bigger than 0, is far to the right of this figure, that the output of logistic regression becomes close to 1. Conversely, if we have an example where y is equal to 0, then what we're hoping for is that the hypothesis will output a value close to 0, and that corresponds to theta transpose x, or z, being much less than 0, because that corresponds to the hypothesis outputting a value close to 0. If you look at the cost function of logistic regression, what you find is that each example, x comma y, contributes a term like this to the overall cost function. Right, so for the overall cost function, we usually we would also have a sum over all the training examples and a 1 over m term. But this expression here, that's the term that a single training example contributes to the overall objective function for logistic regression. Now, if I take the definition for the form of my hypothesis and plug it in over here, then what I get is that each training example contributes this term, right, ignoring the 1 over m, but it contributes that term to my overall cost function for logistic regression. Now, let's consider the two cases of when y is equal to 1 and when y is equal to 0. In the first case, let's suppose that y is equal to 1. In that case, only this first term in the objective matters, because this 1 minus y term will be equal to 0 if y is equal to 1. So when y is equal to 1, when in our example x comma y, when y is equal to 1, what we get is this term, minus log 1 over 1 plus e to the negative z, where, as similar to the last slide, I'm using z to denote theta transpose x. And of course, in the cost, we actually had this minus y, but we just said if y is equal to 1, so if that's equal to 1, I just simplified it away in the expression that I have written down here. And if we plot this function as a function of z, what you find is that you get this curve shown on the lower left of the slide. And thus we also see that when z is equal to large, that is when theta transpose x is large, that corresponds to a value of z that gives us a fairly small value, a fairly small contribution to the cost function. And this kind of explains why when logistic regression sees a positive example with y equals 1, it tries to set theta transpose x to be very large, because that corresponds to this term in the cost function being small. Now, to build a support vector machine, here's what we're going to do. We're going to take this cost function, this minus log 1 over 1 plus z to the negative z, and modify it a little bit. Let me take this point 1 over here, and let me draw the cost function I'm going to use. The new cost function is going to be flat from here on out, and then I'm going to draw something that grows as a straight line, similar to logistic regression, but this is going to be a straight line in this portion. So the curve that I just drew in magenta, the curve that I just drew in purple and magenta, so it's a pretty close approximation to the cost function used by logistic regression, except that it's now made up of two line segments. There's this flat portion on the right, and then there's this straight line portion on the left. And don't worry too much about the slope of the straight line portion. It doesn't matter that much. But that's the new cost function we're going to use for when y is equal to 1. And you can imagine it should do something pretty similar to logistic regression. But it turns out that this will give the support vector machine computational advantages and give us later on an easier optimization problem that will be easier for software to solve. We just talked about the case of y equals 1. The other case is if y is equal to 0. In that case, if you look at the cost, then only this second term will apply, because the first term goes away, right? If y is equal to 0, then you have a 0 here, so you're left only with the second term in the expression above. And so the cost of an example, or the contribution of the cost function, is going to be given by this term over here. And if you plot that as a function of z, so I have here z on the horizontal axis, you end up with this curve. And for the support vector machine, once again, we're going to replace this blue line with something similar. And in particular, I'm going to replace it with a new cost, this flat out here, this 0 out here, and that then grows as a straight line, like so. So let me give these two functions names. This function on the left, I'm going to call cost subscript 1 of z, and this function on the right, I'm going to call cost subscript 0 of z. And the subscript just refers to the cost corresponding to when y is equal to 1 versus when y is equal to 0. Armed with these definitions, we're now ready to build the support vector machine. Here's the cost function j of theta that we had for logistic regression. In case this equation looks a bit unfamiliar, is because previously we had a minus sign outside, but here what I did was I instead moved the minus signs inside this expression, so it just makes it look a little bit different. For the support vector machine, what we're going to do is essentially take this and replace this with cost 1 of z, that is cost 1 of theta transpose x. And we're going to take this and replace it with cost 0 of z, that is of cost 0 of theta transpose x. Where the cost 1 function is what we had on the previous slide that looks like this, and the cost 0 function, again, what we had on the previous slide that looks like this. So what we have for the support vector machine is a minimization problem of 1 over m, sum over my training examples of yi times cost 1 of theta transpose xi plus 1 minus yi times cost 0 of theta transpose xi, and then plus my usual regularization parameter like so. Now, by convention, for the support vector machine, we actually write things slightly differently, or we reparameterize this just very slightly differently. First, we're going to get rid of the 1 over m terms, and this just happens to be a slightly different convention that people use for support vector machines compared to for logistic regression. But here's what I mean. What I'm going to do is I'm just going to get rid of these 1 over m terms, and this should give me the same optimal value for theta, right? Because 1 over m is just a constant. So, whether I solve this minimization problem with 1 over m in front or not, I should end up with the same optimal value for theta. Here's what I mean. To give you a concrete example, suppose I had a minimization problem that minimize over a row number u of u minus 5 squared plus 1, right? Well, the minimum of this happen to know the minimum of this is u equals 5. Now, if I were to take this objective function and multiply it by 10, so here my minimization problem is min over u of 10 u minus 5 squared plus 10. Well, the value of u that minimizes this is still u equals 5, right? So multiplying something that you're minimizing over by some constant, 10 in this case, it does not change the value of u that gives us, that minimizes this function. So in the same way, what I've done by crossing out this m is all I'm doing is multiplying my objective function by some constant m, and it doesn't change the value of theta that achieves the minimum. The second bit of notational change, which is just again the more standard convention when using SVMs instead of logistic regression, is the following. So for logistic regression, we had two terms to the objective function. The first is this term, which is the cost that comes from the training set, and the second is this term, which is the regularization term. And what we had was we controlled the trade-off between these by saying, we wanted to minimize a plus, and then my regularization parameter lambda, and then times some of the term b, where I guess I'm using a to denote this first term, and I'm using b to denote that second term, maybe without the lambda. And instead of parameterizing this as a plus lambda b, we could, and so what we did was by setting different values for this regularization parameter lambda, we could trade off the relative weight between how much we want to fit the training set well, that is minimizing a, versus how much we care about keeping the values of the parameters small. So that would be the parameters b. For the support vector machine, just by convention, we're going to use a different parameters. So instead of using lambda here to control the relative weighting between the first and second terms, we're instead going to use a different parameter, which by convention is called c, and we're instead going to minimize c times a plus b. So for logistic regression, if we set a very large value of lambda, that means give b a very high weight. Here is that if we set c to be a very small value, that corresponds to giving b a much larger weight than a. So this is just a different way of controlling the trade-off, or just a different way of parameterizing how much we care about optimizing the first term versus how much we care about optimizing the second term. And if you want, you can think of this as the parameter c playing a role similar to 1 over lambda. And it's not that these two equations or these two expressions will be equal if c equals 1 over lambda. That's not the case, but rather is that if c is equal to 1 over lambda, then these two optimization objectives should give you the same value, the same optimal value for theta. So just filling that in, I'm going to cross out lambda here and write in the constant c there. So that gives us our overall optimization objective function for the support vector machine. And if you minimize that function, then what you have is the parameters learned by the SVM. Finally, unlike logistic regression, the support vector machine doesn't output a probability. Instead, what we have this cost function, which we minimize to get the parameters theta. And what a support vector machine does is it just makes a prediction of y being equal 1 or 0 directly. So the hypothesis will outpredict 1 if theta transpose x is greater than or equal to 0, and it'll predict 0 otherwise. And so having learned the parameters theta, this is the form of the hypothesis for the support vector machine. So that was a mathematical definition of what a support vector machine does. In the next few videos, let's try to get better intuition about what this optimization objective leads to and what are the sorts of hypotheses a SVM will learn. And we'll also talk about how to modify this just a little bit to learn complex nonlinear functions.